Hello, welcome to Techie DIY. In today's video I'm going to upgrade the spindle motor on a 3018 CNC machine with a more powerful Mashi-Fit 500 watt model. The 3018 machine that I'm using is a basic model from Banggood that I reviewed in a previous video. It has a Gerbil controller and a 24 volt DC spindle motor. The new spindle motor cost $70, it was delivered packed in foam, and it was supplied with a power supply and an aluminium clamp. The spindle is air cooled with an external fan, has an ER11A chuck and a 3.175mm or 1/8 of an inch collet. The spindle motor body is 52mm in diameter, 208mm in length, and it weighs 920 grams. It's considerably larger than the existing spindle motor, so the Z-axis on the 3018 machine will need to be modified to accommodate it. The power supply is a chassis type. It has an input of 110 to 220 volts AC and a variable output of 0 to 100 volts DC. A potentiometer sets the output voltage, and this in turn determines the speed of the spindle motor. These are the connections on the power supply, but before we wire it up, let's have a look inside. The mains AC power is connected to the top two terminals with the live input protected by a fuse. The AC is rectified by a full wave bridge and the DC smoothed with an electrolytic capacitor. There are two components bolted to the chassis which acts as a heatsink. Firstly, a UF460L, which is a 500 volt 21 amp N-channel power MOSFET, and secondly a U860G 600 volt 8 amp power rectifier. Plastic film is used to electrically insulate them from the chassis. The rest of the components make up a switch mode power supply circuit. The DC output is available from the 3rd and 4th terminals. The 5th and 6th terminals are used to switch the output on or off. The blue preset pot sets the maximum output voltage, and the green connector is used to connect the potentiometer, which controls the output voltage. The back of the PCB has some flux residue, which I'm going to clean off before reassembling the power supply. Next, I'm going to test the spindle motor. A power cable is wired up to the power supply terminals. There isn't an earth terminal, so I'm connecting the earth directly to the chassis. The spindle motor is temporarily mounted on a piece of wood and connected to the motor terminals on the power supply. I've got a multimeter measuring the output voltage, and with the power turned on, the potentiometer is turned to the maximum setting. As expected, the maximum is 100 volts. The way that I'm going to connect the spindle motor to the Gerbil controller is with a relay. This will allow the spindle motor to be automatically turned on or off under program control. The coil of the relay will be connected to the spindle motor output socket in place of the existing spindle motor. The relay's switch contacts are connected to the power supply terminals, and this allows the Gerbil controller to switch on and off the new spindle motor. To mount the relay, I've designed a simple printed circuit board using Eagle, which I'm going to mill later in the video. Next, I'm going to remove the spindle holder and dismantle it so that I can take some measurements. The new spindle holder is going to consist of a pair of 6mm acrylic plates bolted together with spacers. I created the design for the plates in Easel, and you can find a link to it in the video description. The new holder also uses 4 flange linear bearings and a lead screw with an anti-backlash nut. Next I'm going to reassemble the 3018 machine, and while I'm doing that I'm going to make some improvements. The first is to install thrust bearings on the stepper motor shafts. When I previously reviewed the machine, I found that the stepper motors had quite a lot of play, which affected the machine's accuracy. To fix this, I'm installing a penny washer and a thrust bearing on each stepper motor shaft, sandwiching them between the stepper motor body and the blue shaft coupler. The penny washer is there to stop the thrust bearings falling into the wide shaft opening. The second is to turn the spindle holder upside down. The reason for this is that the spring in the Z-axis anti-backlash mechanism normally pushes the spindle holder downwards. When the end mill hits a hard surface, the spring compresses and takes up the play from the lead screw, a little bit like a shock absorber, and that makes it quite difficult to accurately set the Z-axis height. By turning the spindle holder upside down, the spring now pushes the spindle upwards and eliminates the small amount of play from the lead screw. I'm also adding a very simple air cooling attachment, which is just a pipe and a tube connected to a compressor. This is attached to the mounting threads on the bottom of the spindle motor. Okay, so now let's mill the printed circuit board. I've loaded the JPaddy workspace from the Chili Pepper website and run a serial port JSON server. Now I can scan for the server and connect to it. Drop the Eagle file into the workspace, and after a few changes we're ready to run an auto level. I'm using mitre adhesive and painter's tape to attach the blank PCB material to the spoil board. The probe leads are connected to pin A5 and ground on the controller. Then I run the auto level, which uses the probe to measure the surface height in a grid and modify the G-code to account for surface height variations. Next, the PCB is milled using a V-bit. And the holes are drilled. Now we can cut the acrylic plates. I'm using a 2 flute 3mm bit with a 200mm per minute feed rate, 120mm per minute plunge rate, and 0.5mm depth per pass. I'm using 6mm thick cast acrylic sheet, leaving the protective backing in place and attaching it to the spoil board with mitre adhesive and painter's tape. It's important to use cast acrylic, as extruded acrylic is difficult to mill. To send the G-code to the machine, I'm using Candle. Next, I'm going to manually countersink the 4 mounting holes for the anti-backlash nut. The countersink bit requires a larger 6mm collet. And I'm just using the jog keys to find the right depth. The next job is to remove and dismantle the spindle holder. I'm going to make a new spring to replace the one supplied with the anti-backlash nut. This will allow me to adjust the strength of the spring to properly support the weight of the new spindle motor. Now we can assemble the new spindle holder. Now we can install the spindle holder into the carriage. Reinstall the stepper motor. Slide the whole assembly back onto the rails. Plug in the stepper motor cable. And check that the axes operate correctly. The power supply and the spindle motor are connected with a cable. And then the spindle motor is tested by turning on the power and changing the potentiometer setting. Next, the components are soldered onto the PCB. A length of cable is soldered to a DC barrel connector, and the other end is connected to the PCB input terminals. The cable is plugged into the controller, and the operation of the relay checked by turning the spindle on and off from candle. A second cable connects the output terminals of the PCB to the on-off terminals of the power supply. And finally, with the power supply switched on, the spindle motor is tested. Okay, let's try it out. I'm going to cut out a hose adapter from MDF using a 3mm 2-flute end mill. Next, I'm going to cut out a bracket from 1.5mm aluminium sheet using the same 3mm 2-flute end mill. And finally, I'm going to resurface the spoil board using a 22mm surfacing bit. Overall, this has been a very worthwhile upgrade to the 3018. It now cuts much quicker than it did before. I'll leave a link to the parts and the design in the video description. Thanks for watching, and I'll see you again next time.